Welcome to today's quantum space-time seminar. Today we are very happy to have Petr Kravchuk, who was at the Institute and now he has moved to Simon Center. He's going to tell us about conformal bootstrap with spinning correlators and Gross-Neveu-Yukawa models. Over to you, Petr.
Thank you, Abhijit, for the introduction, and thank you very much for the invitation to give a talk. So I'll be discussing today some work in progress and some work I've done in the past with this group of collaborators mainly. And I'm going to discuss somewhat, the work in progress is about bootstrapping Gross-Neveu-Yukawa models, which I'll describe, but perhaps not in as much detail as I would like to, because it's a work in progress and there are like some things which are still in motion. And besides that, I'll discuss some techniques and tools that we have developed over the last several years for performing such bootstrap studies. And kind of the main message that I want to convey is that these tools are out there, they're open source, you can just download and use them, and also do interesting numerical bootstrap studies. So hopefully that will be clear. And hopefully it will be clear that it's not possible without too much pain. So let me start. The plan of the talk is going to be as follows. I'll first briefly mention what are the Gross-Neveu-Yukawa models and some motivation for them. And then I'll describe our current sort of preliminary results for their bootstrap. And hopefully this will serve as a motivation for the rest of the talk. And we shall first give a quick reminder of how numerical bootstrap works in general, and then I'll discuss what goes not wrong, but what becomes more complicated when you start studying correlation functions of operators with non-zero spin, and so what are the problems and how do we solve them, and what are the tools that we now have for treating them. So let me start with the Gross-Neveu-Yukawa models then. So Gross-Neveu-Yukawa models are models of n Majorana fermions, psi I, and one real scalar sigma, which interact with each other by Yukawa interaction, and the field sigma also has a quartic self-interaction. Now, if you tune the mass appropriately and look at the RG flows, you can find that there is a non-trivial IR fixed point with non-zero values of both couplings, and this fixed point describes some interesting non-trivial CFT, and people, although I'm not going to discuss this at all, some people think that it might be relevant for various condensed matter systems. So for example, it is discussed that this theory for n equals 8 might be relevant for a phase transition in graphene. So,
sorry, could I ask a quick question?
Yes, sure.
Yeah. So why don't you have a sigma cube term? Is that because you're imposing a symmetry on the problem?
Yes, I should say that it has this Lagrangian special because it has a symmetry. It has parity symmetry under which sigma is parity odd. So psi bar psi is parity odd, and multiplied by sigma it's parity even. So this is this term is invariant, and then since sigma is in even powers, it's also invariant. So that's why we don't have sigma cubed, and that's also why we don't have a mass term for the fermions.
Okay, and one more question, please. If at least at large n, it would appear that sigma has dimension 1. Because it's like a Lagrange multiplier field for psi bar psi. So if I got that right, the sigma to the 4 term sounds sort of odd because it looks like a non-renormalizable term, like an irrelevant kind of deformation of the. So.
Well, in free theory, sigma has dimension 1/2 in 3 dimensions, so it's this term is relevant, and.
Oh, I see.
So you should think about this Lagrangian as more of a perturbative Lagrangian.
I see. Now I understand. It's just an ordinary scale. It's yeah. I didn't see the kinetic term for sigma. Thank you.
Yeah, sorry. Yeah, it's kinetic.
Yeah. Okay. So just a theory of scalars coupled to fermions. Okay. Thank you.
Yes, precisely.
Yes. Okay. Okay. Thank you.
So for n equals 1, this I think it's believed. I mean, it's expected that for n equals 1, this conformal theory that you get is a supersymmetric Ising model, I should say. And so that's actually a reason why I won't be talking about n equals 1, because it's easier to study using different ways. So yes, so our goal is to apply numerical bootstrap techniques to this theory and get some bounds on scale dimensions of the fields and whatever you would like. So this is not the first time when people want to do this. So there have been 2 previous papers when people did numerical bootstrap with this theory in mind. So in this paper from 2015, these guys looked at 4-point function of a single Majorana fermion. So clearly, since it's a single Majorana fermion, there is no way to tell what n is. For any n, you have at least 1 Majorana fermion. So this bootstrap kind of puts bounds on all these theories simultaneously. And what they found in that work is that the best they could do is to find some exclusion plot in the plane of delta sigma and delta psi. So there is some allowed region, and if you make appropriate assumptions, then this allowed region has a kink, and but the position of this kink, it depends on one of the assumptions that you make, and this assumption is about the scaling dimension of subleading parity odd scalar. So kind of if you take this kink seriously, then what it really gives you is just some relation between delta sigma prime and delta psi, instead of a kind of definite values for these parameters. Actually, two relations.
Sorry, and you probably said this, but so should I think of this theory as like you're looking at you're looking at the conformal theory? Should I think of this as like a theory of one Wilson-Fisher boson interacting with free fermion?
Well, no, I guess I guess it is probably possible to. Well, I'm actually not sure, but I haven't thought about this carefully. You can imagine that it might be possible to take Wilson-Fisher boson, couple it to free fermion, and float to this fixed point. But it's not necessarily what I'm saying. I'm just saying that this Lagrangian, you can find, let's say if you do 4 minus epsilon expansion, you can find the fixed point with both non-zero, both G and lambda, and that will be a CFT. So
I see. Yes. So, but suppose G was set to 0 to start with. Then
yes,
we would have a conformal theory, which is just the free fermion and the Wilson-Fisher boson, right?
Yes.
So in some sense, this is okay, but G will be, yeah, okay, fine. So in that double theory, is sigma psi bar psi a relevant operator of that double theory?
Sigma psi bar psi. So yes, it's relevant.
Good. So then it sounds plausible, right? That you start with that Wilson-Fisher plus turn on that relevant operator and it'll flow to this point. Okay.
Yes, it does. Indeed.
Okay. Thank you.
If I understand the physics of this model correctly, the CFT that we're looking at describes the following situation. So for large negative mass, you're going to have, for large negative mass squared, you're going to have a spontaneous symmetry breaking, which will give expectation values to sigma and mass to the fermion. And then for large positive mass, it's not going to happen. So we're just looking at the phase transition between this, presumably.
Right. So at m equals 0, at G equals 0, it's like Wilson-Fisher boson plus free fermion. And then you could, right. It's always keeping m to 0. You could turn on the G deformation and try to flow, right? Is it? Yeah. Okay, fine. Thank you.
I mean, I'm also kind of approaching this theory from the point of view that, I have not thought too carefully about like getting it in various ways. It's just there is one definition, and I'm trying to.
I understand. I just want to get a mental picture of it. One more question.
Yeah.
If n is taken to infinity, then presumably this model is solvable.
Yes.
Okay, great. Yeah, thank you. In that limit, in the limit that n goes to infinity, what are the dimensions of sigma and psi?
sorry, I need to remember. Sigma, I think, is 1. Give me a second. Large N, sigma is 1, and psi is also 1.
Wonderful. So it's like the kinetic term for sigma, and that limit becomes irrelevant.
Yeah. Yes.
Right. So also the okay. Thank you.
Okay. So let me go on. So these guys studied just single fermion, and they were getting kind of a continuous family of kings, and they couldn't really pinpoint different theories, but it gives a good indication that something is there. And so a bit later, they studied a 4-point function of 4 fermions, and now they could specify how many fermions they have, and they were getting a similar plot, but now depending on the value of n, the kind of the position of king took some places, discrete places, and the position of this king was reasonably consistent with like large n and epsilon expansions and other things that people have done for this series. But these kings aren't super sharp, and also king is just a king. It's not very definite, and what we would like is really to isolate this as an island, so to have an island in our exclusion plot and not some king in the larger block. And because islands give definite inequalities for the scaling dimensions, so on. So what we're doing for that is we're considering now a much larger system of correlation functions. So we're considering crossing symmetry for which involves sort of 4-point functions of 4-point function of sizes before people have considered, but we also include the 4-point function involving the field sigma itself, and also the operator epsilon, which is roughly speaking sigma squared, and it's just defined as the lowest dimension parity-even scalar in the theory. And so there are 7 different correlation functions. So the only probably kind of maybe a bit surprising one is that this one is non-zero, but this is because sigma is parity odd, and parity is really the space parity. So there is a kind of, there turns out that there is a invariant 4-point tensor structure which involves sigma and 2 psi's. So this 4-point function is not trivially zero. And so these 4-point functions also include lots of OPs. If you start studying crossing symmetries, you have to take OPs between sigmas, between psi's, psi's and scalars, and etc. And if you look at all the possible OPs, you find that well, there are various operators appearing. So these are the operators that we can reason about in our setup. And these in psi-psi channel, these include various operators of various spins of both parities in trivial representation of the symmetry group here. And then they also include the representations traced in spin 2 symmetric tensor of the ON global symmetry, and in the antisymmetric presentation of ON global symmetry. So in particular, this class includes sigma and epsilon, while also we have other OPs. So we have OPs of psi with scalars, which gives family fermionic operators, and these fermionic operators also have a parity label. So there is, for example, this lowest spin, the spin 1/2, there is psi itself, and also another spinner chi, which has kind of parity opposite to that of psi. So this is, for example, something like chi would be something like psi times sigma. Then, of course, we have the scalar OPs, which are fairly straightforward as usual. And this is just to show that all these different OPs have kind of overlapping sets of operators. And so all these 4-point functions are kind of mixed together into one system. So let me then tell you what kind of results we are getting so far with the setup. And I'll just show you one preliminary plot for n equals 2. So in this plot, this is 3-dimensional plot with delta psi, delta epsilon, and delta sigma. And you can see that we're getting some compact islands. which are shrinking. So different shades of purple here correspond to different values of Nmax. And Nmax is a parameter which determines how many equations we are considering, how many crossing components of crossing equations we are including. So you can see that it's getting smaller. These islands are not particularly small by bootstrap standards, perhaps, but they're reasonably nailing down this scale dimensions reasonably precisely. Another interesting feature, which is something we're trying to understand a bit more, is that, well, to make this islands, we have to make some assumptions. So, for example, there are some assumptions which we make on various operators in various channels, which we are reasonably confident about. For example, we assume that the second to lowest dimension parity-even scalar has a dimension greater than 3, which is just a statement about the fact that it should be irrelevant. And this comes from our expectations about the structure of the fixed point in the phase diagram. But there are also an assumption which turns out to be particularly important on the dimension of the second to lowest parity-odd scalar. And it turns out that this shape of the island is very sensitive to this value. So, for example, this purple plots are done assuming that its scaling dimension is at least 2.5. But if you assume that its scaling dimension is at least 3, then for Nmax 8, so it corresponds to, so it's analogous to this kind of second to largest island. This already shrinks the island to this small region here. So here it's the same plot on each side. And so we see that it's very sensitive, but we don't have very good data on what the scaling dimension of this guy should be. And we feel that 2.5, from what we know, is quite reasonable assumption. And we would like to say that it's actually 3 for at least larger values of n, but it's really hard to tell because all we have available is things like epsilon expansion and Argent expansion, and it's not very clear how to make a clean argument. So far, we're just exploring what happens for various values.
Sorry, could you tell me again what which operator sigma prime was?
So sigma prime is the second to lowest parity-odd scalar.
And that's roughly sigma psi by psi? Oh, no, that's parity even. Nice. Sorry. So could you give a rough Lagrange description of what you expect it to be? Let's say it larger.
I think it's more like sigma cubed. Sigma cubed, sorry.
Sigma cubed, I see, sigma cubed.
Yes.
I see, thank you.
So it's large and it has, so in principle,
it's like dimension 3, yeah? Yeah.
Yes, it's dimension 3. So like one reason why we are entertaining the idea that it's greater than 3 for all n is that it has positive 1 over n correction.
Right.
So its scaling dimensions large n is 3 plus positive 1 over n. But I mean, it's not guaranteed that it's going to remain positive for finite n.
Thank you. And the scaling dimension for psi seems pretty close to 1.
Yes.
And the scaling dimension for sigma is
around 0.6.
0.6. And what is that for Wilson-Fisher theory at n equals 2? Do you know? Is it about the same?
For Wilson-Fisher, all low values of n are around 0.52, if I remember correctly. So the Ising is 0.518, and I think n equals 2 is not much higher, but I don't remember.
Okay, but it's fine. Thank you.
Sure. But you can also, like, it's kind of similar to Wilson-Fisher. You see the delta epsilon is compared, like, has large anomalous dimension compared to delta sigma, in the sense that it's like not close to delta sigma. So it's similar to what happens in Wilson-Fisher as well. So delta sigma here is like around 0.75, 1.75, whereas you would probably expect it to be 1.3 if you just took 2 delta sigma.
What are the relevant operators of the theory? You, I think, mentioned, but I didn't catch.
Fermion mass and boson mass, I think.
So fermion, yeah, the parity even is only the boson mass. Yes.
I see. And also this and the parity odd, if you include that, then there is how many?
The fermion mass, right?
Yeah, I think then there are two, but yeah, there are also other like global symmetry representations, so you can break global symmetry, but then that will add more.
I see. Sigma is also relevant, right?
Sigma is the boson mass operator.
Yeah, so sigma is
Sigma is the mass operator. No, but then epsilon is also relevant, isn't it? Sorry, no, sigma is not the boson.
Sigma is just the field.
Yeah, the field.
Epsilon is the boson mass. Yes, so epsilon is like 1.75.
Sorry.
But sigma, you can also deform by sigma, right? If you want to break parity.
You can also you can try deforming by sigma, yes, but this will break parity.
Yeah, and the sigma prime is relevant for some and irrelevant for the other, for the higher.
So it's unclear. I'm not sure if it's clear.
Okay, I see. Okay, fine.
Sigma prime breaks the parity symmetry, so it's a different analysis.
Thanks.
Okay, so just
sorry, but could you say a little bit what does deforming by sigma do? I mean, what would you expect for such deformation? From a Lagrangian point of view, let's say, or from any other point.
Well, I'm not sure, right? Because it breaks parity symmetry, and I'm just not sure what is the phase terms. Yeah, I have never thought about it. So, yeah.
So, but if you look at the analogy with the free scalar field, this is like deforming by the spin operator, like by phi, right? So it's what we do when we turn on, I don't know, magnetic, like that magnetic field kind of thing, right?
So right? This gaps out the theory.
I would imagine. What? Yeah.
Okay.
Oh. Yeah. Right. So I just want to point out that like while we do have a quite complicated setup with like lots of crossing equations, we do end up isolating this theory, which is quite nice. And so we're pretty happy about this. So far, we're working on pushing to higher Nmax and also exploring different things and working with technical issues. Also, I just wanted to point out that n, the number of fermions, is of course a free parameter. It doesn't cost us anything to change it. I mean, it costs us running new bounds, but it doesn't make the problem more complicated. And so far, we're focusing the values 2, 4, 8, because 4 and 8, I think, are most interesting for condensed matter, and 2 is 2. It's small. But if you think that some other values are interesting for some particular reasons, I would definitely like to know about that.
So for n equals 8, there are experimental data. Is there?
Yeah, I don't think there is experimental data. There are suggestions, as far as I understand, that it might be relevant for some phase transitions, but I'm not sure if we have experimental data. There is Monte Carlo data for various values.
Okay.
But yeah.
And sorry, why did you allow for flavors for the fermions but not for the bosons?
It's just a particular, it's just one model. You could imagine adding bosons, then it's going to be more complicated. Yeah.
Yeah.
Sorry, how would the Yukawa term preserve symmetry?
Maybe that's.
Oh, you can give them different representations. Like you could give sigma adjoint.
Yeah, then you could. But it needs to be.
Maybe not adjoint, but yeah, you have to think about. But I imagine that there is a more complicated theory, more complicated with several scalars. But okay, so that's what we get, and I just, in the remaining time, we'll try to quickly tell you how we ended up here. And that is mostly a story about how we were fighting absence of nice tools and formulas and trying to get them and to make projects like this less painful. So for this, let me start with a numerical bootstrap reminder. Just remind you how numerical bootstrap is done, but of course, everybody is probably relatively familiar with this, so I'll just be very brief. So if you focus on the simple example of a scalar for point function, then the first step that we do is we solve conformal symmetry constraint for this whole point function, which tells us that we have some relatively simple prefactor and then just a function of the cross ratios. Then the OP expansion between 5x1, 5x2 induces a conformal block expansion for this function of cross ratios. So we have that this function is equal to sum over all local operators, the P coefficient squared, times special functions, which we call the conformal blocks. And a useful way to think about this OP coefficient is that this is the coefficient that appears in the 3-point function phi phi o. So if we solve conformal symmetry constraint for this function, we find that there is a one-dimensional space of solutions. So we can choose a basis element, and the coefficient that actually is realized in the theory is the P coefficient. So this is the conformal block expansion, and the crossing symmetry is a statement that taking a P between, say, phi1 and phi2 is essentially the same statement of P between phi2 and phi3. And in terms of this function g of z is a bar, it's just a statement that it should satisfy some particular symmetry equation. So the bootstrap then proceeds by taking the conformal block expansion, plugging it into the crossing symmetry equation, rearranging everything to one hand side, and writing this as a sum of some functions of z bar times P coefficient squared equals 0. Then we truncate this system of equations labeled by z and z bar to find dimensional system by taking derivatives with respect to z bar at z bar equals 1/2 and limiting the total order of this derivatives by some function of n max, which is the parameter I discussed before. And then the analysis proceeds by observing that the P coefficient squared are non-negative, so we can apply linear programming duality to this equation. And basically what we start doing is looking for a bunch of coefficients alpha and n, such that if we sum these derivatives with these coefficients, then the sums are going to be non-negative for all delta and j in some set of quantum numbers. And if you manage to find such a functional alpha, then plugging this into the crossing symmetry equation, we find that it cannot be solved because we get a sum of non-negative coefficients with non-negative functions after the plugging for alpha. And this implies that the equation can be solved non-trivially. And so we reach the conclusion that either there must exist operators which are outside of this spectrum S that we assumed, or that the value of delta phi that we have chosen cannot be realized for operators living in the spectrum. And yes.
Sorry, can I ask a general basic type question?
Yeah.
So why is it that in the bootstrap, the numerical bootstrap, one expands around this particular point to get the functionals rather than some other point, or rather than constructing some other type of functional?
So this is a great question. People have tried different things. So this particular approach, taking z and z bar equals 1/2, what it ensures is that the cross ratios are the same in two channels. And so the approximations, so this function f is the sum of two functions. And like one is coming from, say, S channel and another is coming from T channel. And taking z bar equals 1/2 ensures that they have the same cross ratios. And since they have the same cross ratios, then the approximation used for the one is also good for the other. People have tried, and this turns out to be technically useful when using SDPB. People have tried, for example, just evaluating this equation at a bunch of points in the region where this equation converges. And this also works. It doesn't seem, well, at least when people have done what they have done, it didn't seem that it converges, that it works much better. But of course, there's been recent work on analytic functionals, and analytic functionals are like integrals of this equation with respect to z bar over some regions, and you can sometimes construct actually exact extremal functionals for some optimization problems. And that, of course, does not just include z equals z bar equals 1/2.
So have the analytic functionals been used for numerical bootstrap?
Well, there has been some exploration by Miguel Polish and I think somebody else in one dimension, but it's so far not very clear how to do it in high dimensions. I'm not working in using numerical bootstrap. So
yeah, but this particular reason that the cross ratios are the same. That criteria would fix a line worth of points, right? There are many points with that property, but somehow this is the one that works the best.
Yes, so you want z equals the bar because this is the point which has positivity conditions. So basically what you're trying to do is you want to ensure this inequality, and you want to ensure it for like whole lots of spins, and the conformal blocks involve Gegenbauer polynomials. And these Gegenbauer polynomials have index which is spin, and the argument is cosine of argument of z. And if the argument of z is non-zero, then these Gegenbauer polynomials can oscillate in sign. What this means is that I think what happens in practice, I'm not sure I have done this experiment myself, but I think if you try to do this in practice, what happens is that you try to impose this inequality for like some set of spins, and maybe it works out for this set of spins, but then it starts oscillating at higher spins. So you cannot, like, you're failing to actually come up with something which is positive for many spins. Whereas when you work at z equals z bar, then in that case, it's nice, and if it's positive for like first 50 spin, let's say, then you can check that it's positive for.
Okay.
Like you can ask, this is like z equals z bar equals 1/2 is like just one sort of z2 fixed point of crossing symmetry. There is also z3 fixed point.
Yeah.
E to the I pi over 3 or something. That has the same problem, that it's hard to solve for this positivity constraints. So, and yes, when you look for this coefficients using this software is DPB, which is now kind of the standard, and it has been developed by Walter Landry, who is software engineer hired by Bootstrap collaboration, and it's now very powerful, can work on clusters, and it's great, and everybody should use it, and it's amazing. So of course, I have just described the scalar 4-point function. Our setup is much more complicated.
Sorry, just one more question about this SDPB, just kind of a practical question. So could you say briefly, what does using it mean? So is it like, everything is there and we just have to input the problem that we are interested in? So, I mean, if you could say a few words about how this could actually be used, maybe you will say it later, but to what extent is the package ready, and what is the input to that, and then.
So you're asking if you have never used it, like what do you
yes,
do?
so if I want to use it, then how much,
So it's like it's a collection of maybe, like, there are two main programs which you can just think of. One, it's just like you run one and then you run the second one. You have to get them installed on your computer or on your cluster. There are various ways of doing this. It's not very hard. And then what it accepts as input, it accepts a semi-definite problem, which is not conformal bootstrap necessarily. It's just a semi-definite program, which is of the form that you have some basis of polynomials. You're looking for linear combinations of these polynomials. well, you have a basis of polynomial matrices, and you're looking for linear combination of these polynomial matrices, which are positive semi-definite for all positive values of the argument of the polynomials. And so this is the rough form of the semi-definite program that you input, and it just solves the semi-definite program. So it's not about bootstrap necessarily. It's a semi-definite solver which is optimized for working with these constraints which are polynomials and parameter. And the reason why it's polynomial is because we use polynomial approximations for the conformal blocks. So we approximate polynomial conformal blocks by polynomial of delta multiplied by some positive function. So you can factor
the block
out this positive
needs to be
function.
fed into that.
Yeah, you need to compute the conformal block, and then you kind of pull out a polynomial from this conformal block, and then you feed this into the SDKB, and then SDKB does its magic. So it's just a solver. It doesn't know about conformal bootstrap in this sense. It just solves a particular type of semi-definite programs on half-line.
Thank you.
But I'll say a bit more about what to do if you want to know conformal blocks. So now our setup is more complicated than this simple 4-point function. And so in particular, we have at least not one operator, we have 3 different operators. We also don't have just one 4-point function, we have 7 4-point functions, and doing more crossing equations that they satisfy. And these are sort of mild problems, and they are well known how to deal with. But the more kind of annoying problem is that psi has a spin, so it has the Lorentz index alpha, which carries spin 1/2. And this just introduces complications simply because the conformal blocks become more general functions, and you need to compute them somehow, and you need to compute a lot of them. So we have these complications, and sort of you can roughly split them into 2 problems. So one problem is just an annoying problem. It's the problem of bookkeeping. You just need to keep track of all the equations, of all the matrices, of all managing all the computations in the cluster, etc. You just need to keep this whole ton of equations together. And the more mathematical problem is to deal with this spin, so to compute the new conformal blocks and so on. So the annoying problem for us, at least, is solved in practice by a family of Haskell of some computer programs, of some libraries written in language Haskell. Here are their names, which they're mostly written by David Simon-Staffen, and there are also some contributions from other people in our collaboration. And it takes care of this whole stuff, of all the bookkeeping, sending things to cluster, running SDKB, producing the input that SDKB understands, taking your equations, and so on. So, but what we need to supply it with is a way of computing conformal blocks. So it doesn't know how to compute conformal blocks on its own. But this is a very useful set of tools, and it's open source, it's online, you can download it, you can use it. It's a bit, has a bit of a learning curve, but it's very powerful. And you know, if you're interested, you can ask me, and I'll be happy to help you get started. So this leaves us with this mathematical problem of understanding spin. So let me move on to this. And the problem with spin is that just when you add spin, you add indices, and when you add indices, you start getting more and more indices everywhere. So in 3 dimensions, I'll just focus on 3 dimensions here. We can describe spin by operator O by a bunch of symmetric spinor indices, and I'll be mostly omitting them, and you can think that I'm just contracting them with some polarization spinor and keeping dependence on X and on the spinor. And so when you start working with operators with spin, you can start looking at 2-point function. 2-point function isn't that bad because there is always just a unique 2-point function for any operator in CFT, and you can write an explicit expression. There doesn't seem to be much to it. But then when you start looking at 3-point functions and you get this 3-point function, you start solving constraints of crossing symmetry of conformal invariance. And you realize that the space of solutions is now not 1-dimensional, it's some finite dimensional like maybe 10-dimensional, 100-dimensional, depending on the values of the spin space. And so the 3-point function is now described by some finite set of p coefficients, in general containing more than one coefficient, and some finite basis of basic solutions. And the same thing, of course, happens for the 4-point functions, except that now the coefficients are allowed to depend on z in the bar. So we have several functions g, distinguished by index I, which describe a single 4-point function of spinning operators. And so since this all happened, if you now start discussing conformal block expansion, then of course we have to write conformal block expansion for all our functions gi. So this means that the conformal block should also have this index. And they obviously should also depend on all the coefficients, all the p coefficients, which now carry this index a and b. And so these indices have to be contracted to something inside the conformal block. So we now have this larger family of special functions that we need to compute if we'd like to do some particular bootstrap problem with spinning operators. So this is what we'd like to do. We'd like to compute the special functions. And there's been plenty of papers written about how to do that. But the problem with all that the papers that I'm familiar with is that they give you lots of different algorithms for computing. But all these algorithms essentially reduce to the fact that you decide that you want to compute conformal block for this 4-point function, then you sit down with a piece of paper and you derive a whole bunch of equations. Then after you have derived this whole bunch of equations, you can sit down and input these equations into computer and teach the computer to compute this particular conformal block. And then if you tomorrow need a different conformal block with different choice of spins, then you need to do this whole procedure again. You cannot just sit down once, program a code for all conformal blocks and use it every day. So that's something that we want to solve. We would like to find an algorithm which is parametric in the spins of the external operators. But this produces then a problem for us because then we need to understand the general, I mean, it's not the hard problem, but there's something that we need to understand. It's that we need to understand general classification of these indices A, B, and I. And the reason for that is simply that if you don't know what these indices are for general JI, we cannot explain to the computer what we wanted to compute. So this problem, the solution, you can solve it in many ways. The solution that we use is from our paper with David from 2016, where basically the idea is that if you want to describe a, say, 3-point function, some particular 3-point function, 3 operators, then all you need to do is you need to specify its value for your favorite configuration of 3 points, because if you want to compute it in some other configuration, you can always use a conformal transformation to bring it to your favorite configuration. And then you can ask which values are you're allowed to specify in your favorite configuration. And the answer is that these values should be anything that's invariant under the rotation, under the group of symmetries which preserves your favorite configuration. If your favorite configuration is 3 points lying on the line, at some fixed positions, then in 3 dimensions, then the symmetry that preserves this is rotations around this line. And so in this favorite configuration, what you need to do is to specify a polynomial in the polarization vectors. And we just choose as the basis polynomials which have definite eigenvalues when the two rotation is acting on S1, on S2 and S3, and this eigenvalues are Q1, Q2, and Q3. And the condition that the polynomial should be invariant is just that the sum of this eigenvalues should vanish. And of course, these eigenvalues have to lie in the respective representation, so they range from -chi to ji. And the same thing you can do for the 4-point function, 4-point tensor structures. Now the only difference is that you have to put them on a plane in some generic, and it's one operator. You cannot constrain where it is. But there is no symmetry to respect. There is only parity symmetry which preserves the plane. So there is no continuous symmetry to respect, and there are no conditions on the eigenvalues, except that you can use this parity symmetry to compute the parity of this 4-point tensor structure based on the values of the skews. And so this is some implicit description of the tensor structures, which might seem inconvenient, but in fact, if you think about this, you don't really want to compute tensor structures in some random configurations of points every day. All you need, you want usually some natural properties of this tensor structures, and these natural properties, such as how do these things behave if we start permuting the operators, so what is their transformations under space parity, etc. All these things can be just worked out once, and you have worked it out, and then you can just use them. In this sense, it's a very convenient basis because it always works. So this solves for us the classification problem, but now we know that we understand what the synthesis means. We need to also understand how to compute the conformal blocks. So are there any questions about the classification before I move on to conformal blocks? Okay. So for conformal blocks, we use what is known as the homological recursion relation. And the idea behind it is schematically the following. So if we have our conformal block, we can think about it by definition as sort of this procedure. So I'll put it in quotes because I'm not being very careful here. But we take the state created by operators O1 and O2, and take the state created by operators of 3 and O4, and we insert between them the projection of the primary operator O and all its descendants. So we sum over n, we have descendants which are generated by action of P on O. And because these descendants are not normalized, they have to divide by their norms. In general, these norms are going to be some polynomials of scalar dimension delta O, and polynomials have zeros. So this means that the denominator here can have zeros as a function of delta O, and so conformal block can have poles which are associated with descendants with zero norms. And descendants with zero norms are the null states in Verma modules of exchanged operators. And so if you work through this, what you find is that if you take the conformal block, you factor out some standard prefactor to define a new function h, then this function h satisfies so-called homological recursion relation, which just states that the function h is a meromorphic function with understood poles and behavior at infinity. In particular, it can be written as its value at infinity, which is relatively easy to compute at delta equals infinity, and then sum over all poles. And there are two important features about the residues of these poles. First of all, each of the poles comes with a positive power of some parameter r, where r is a small number in the neighborhood in which we are interested. So just a function of cross ratios. And the second fact is that the remaining part of the residue is proportional to the function h itself with new quantum numbers with the same index for 4-point tensor structure, but the indices for 3-point tensor structures are transformed by some matrix R. And there is lots of components of this equation. So this function, which can be computed, that's not a problem. There are these positions of the poles, powers of this R that appear, this new quantum numbers Ji, and this so-called residue matrices Ri. So these kind of discrete numbers are classified by conformal representation theory, so they're relatively easy to understand. The hard part is understanding this representation matrices, residue matrices Ri, because they are basically, they involve just like a hard calculation. By definition, they are defined by this equation. So the conformally, so the null states of psi are in one-to-one corresponds with some conformally invariant differential operators Di. And the correspondence is that the null state psi can be expressed as radial quantization in this way, where conformally invariant differential operator D acts on O, and then we insert the result at 0 and act on the vacuum. So there are some conformally invariant differential operators Di, and to compute this residue matrix, we need to insert these operators inside the basis of 3-point tensor structures, and then re-expand the result in back in our basis. So it kind of involves a calculation which requires you to understand all the differential operators, so to understand all the null states. It requires knowing more or less explicit expressions for all the 3-point functions and being able to expand. So in general, it's a bit complicated calculation. If you, in any particular case, it's easy to do, but if you want closed form formulas for this, then you really have to understand everything. But if you can compute them,
sorry, could you give us one example of this conformally invariant differential operator, please? The simplest example.
So if you have current J mu, then it has a null state. So if you take kind of, it has a null state like this, and this corresponds to conformal invariant differential operator, which sends J mu to, so it sends J mu of x to d mu J mu of x. So it sends a vector operator to a scalar operator whose dimension 1 greater. But this is a very simple one. So it can be generalized to higher spin currents and still remain simple in this case. But then there are like ones which are much more complicated. So this one actually is, its expression is completely fixed by Lorentz symmetry. If you just tell that you want something which has one derivative and takes a vector into a scalar, it's quite simple. And for higher spin currents, it's also fixed in the same way, but there are some families of null states which have differential operators which have some non-trivial coefficients which are not fixed by Lorentz symmetry. They're just some like strange numbers.
I see. So these conformally invariant differential operators are always those that pick out null states?
Yes.
I see.
Well, by null state, I mean the kind of the lowest dimensional state. So obviously, if you take derivative descendant of null state, it's also
the primary of the module of null states.
Yes, exactly.
Okay. Yes. Thank you.
Sorry, but this is for certain operators like J mu. But here, when you're writing this, your delta can be anything, right?
Yes, but here the differential operator is not acting for delta; it's acting for delta I. Delta I is the delta of J in this example.
Oh.
So this differential operator will appear in this residue matrices. I mean, you can use the differential operator, this example, to compute residue matrices, which will appear in this residue of the pole with delta I equals d minus 1, where d minus 1 is the dimension of the observed current.
Nice.
Right. So, but this differential operator is only useful when the representation running in the middle is a short representation. Is this right?
So they only exist when the representation is short.
Okay. Fine. Thank you.
So in this,
the shortening condition that you can impose. Yes, sir.
So this sum consists of which operator? For example, the sum over I, is it just the spin, currents?
So you take your Verma module for the exchange operator. So it's the kind of the lowest weight has some fixed spin, and you can vary delta. So as you vary delta for special values of delta, the Verma module can stop being simple.
Sorry, why is various? Isn't it only one corresponding to that particular spin, the current of that particular spin?
Sorry, I think I'm a bit confused. So we are computing a conformal block for as a function of delta. So we fix J, so we fix J of the operator.
Yes.
And what I'm saying is we fix J, but we allow delta to vary. And we look at the Verma module of this exchange operator at fixed J and varying delta. So for generic delta, this Verma module is going to be simple. It will not have any non-trivial submodule. It will not have any null states.
Yeah.
However, at special values of delta, the Verma module will stop being simple. It will develop a non-trivial submodule, which will consist of null states.
Yeah.
So this delta I are the values of delta for which this happens.
Sorry, that value of delta. Sorry, when the operator running in the middle is symmetric traceless tensor, that would happen for only one particular value of delta, would it not?
No,
or would
it happens for infinite many. it happens in particular. Let's fix j equals 1. Okay.
Yes.
Then it will happen for delta equals d minus 1.
Yes.
But it also happened for infinitely more cases. It's just that all these cases, we don't usually think about them because they correspond to non-unitary values of delta. So this delta i's will be like negative.
Okay.
Or smaller than d minus 1. Okay.
Yeah.
So for example, you can look at the scalars. Scalars, you can have scalars dimension d minus 2 over 2. Then the null state is the Laplacian.
Yeah.
You can look at scalars of dimension 0. Then the null state is just derivative dx of phi is a null state. D mu phi is null state for any mu if the dimension of phi is 0.
Yeah.
So it's similar to like 2D VRL modules. There are also infinitely many values of h for which they degenerate.
Yeah. Thanks.
Okay. So yeah, the point is that if we manage to compute this, sorry, I think I'm running out of time. Should I wrap up quickly or?
Usually, Peter, we are flexible with time if it is not an issue on your side, but maybe it might be.
I'm happy to finish. I think there are interesting questions, and I don't want to rush if you.
Yeah. Okay. Yeah. So that would be great. Yeah, because because there is a little bit of a back and forth, so it ends up usually over times.
Okay, so I'll continue, and if you feel like I should wrap up soon, you just tell me. I don't think I have that much left. So yes, if you can compute this RIs, that's the point. Then we can understand the right-hand side. I mean, we understand this term, we understand these terms. We don't know this function, but this is the function we're trying to compute. So what you do then is that if you understand all the coefficients in this recursion relation, you just start, you write the right-hand side, so you don't know these guys, so you plug them in again from this recursion relation, right? And because here you have r to the positive powers, that kind of starts delaying your lack of knowledge to higher and higher powers of r. And repeating this again and again, you can then generate a power series expansion in powers of r without knowing from the beginning what h is. Okay. So it's a way to, this equation is a way to generate power series expansion of h in powers of r. Provided, of course, that we know what these coefficients are. And again, people have written papers about these coefficients, and there are various ways to computing them. The trouble is they are not parametric in the external spins. For any choice of external spins, you can sit down and you can derive the formulas for these matrices and put them into the computer, but they're not closed form expressions which work for all external operators. So more recently, in 2019, we managed to compute these coefficients, and now we have them in closed form for any operators in V equals 3. And the logic for this is that the expressions in position space with conformal invariant differential operators are complicated. They're simple for some families, but for other families, they're complicated. It turns out that all of these expressions are equally simple in momentum space. And the reason for that is basically that you can do a little trick in momentum space. So let's say we apply this differential operator to some primary operator O, and we would like to compute the result at some momentum P. So then it's an operator with spin, so it has a bunch of indices. So then we can choose, we need to choose an index, or we need to choose a basis of indices. So a convenient basis of indices is just labeling different projections of spin onto P. So it's like a little group index. It tells us about representations with respect to rotations around the momentum. So if we agree that M means this, so M means projection of spin onto direction P, then it turns out that the dilatation symmetry and Lorentz invariance fix the action of this differential operator to be very simple. It just takes the same component of the original operator, multiplies by some number, which depends on M and the differential operator, and multiplies it by some appropriate power of P, which is just related to the order of the operator. And that's it. That's all it does. And the reason for that is that M has to be the same on both sides, because you can rotate both sides around P without changing P. And so the projection of spin has to be preserved. And the power of P is fixed by, of course, the rotation symmetry. And so that's what happens. And what we have not solved by writing down this equation is the special conformal invariance of this operator's DI. So special conformal invariance in the momentum space has to be imposed separately in the scalar, but you can do this. And then what it leads to is to the recursion relation in this coefficient dm. So it relates coefficient dm and dm minus 1. There are some coefficients in front which you can compute there, like some simple square root of some degree 2 polynomial or something like this. But importantly, you also get just two, not one, but two such relations. And most of the time they're incompatible. And this means that most of the times these differential operators do not exist. Where most of the time means for most values of the scalar dimension of O. And they only exist for this special discrete set. But in any case, you have these two equations. You can figure out when they're compatible, and you can use it to solve for these coefficients. And using compatibility condition, you find that there are 4 infinite families of these differential operators, and you can compare it with the known classification of this conformally invariant differential operators and see that they match. And so in this way, and the expressions that you get are very simple. They're like square root of some programmers, which involve M and I, basically. So that's what you get. And so we know now a nice expression for all the conformal invariant differential operators. Now we would like to compute the residue matrices, and well, to compute them, we need to use this definition. So we need to learn how to act with these differential operators on our 3-point tensor structures. So for that, we need to be able to put them in momentum space, which sounds like stupid, like something complicated. But in fact, you can cheat a bit, because you don't need to compute this full 3-point function for generic x1, x2, and for any momentum. All you need is you need to compute it enough so that you can apply this action, and so that you can compare the left-hand side and the right-hand side to extract these values. So in particular, to act as D, you just need to multiply by some stuff. So it doesn't matter what x1 and x2 are. So you can choose them for your convenience, and just one choice is sufficient. So a convenient choice turns out to be to choose x1 to be 0 and x2 to be infinity. So if you don't go to momentum space yet, and you just put the third operator at some position x, then whatever this 3-point structure is, it should depend only on x. And there's variance and rotation symmetry to help us understand what it can be. And basically, it has to be some power of x times the polynomial of x, and we can expand the polynomial into trace symmetric combinations of x with different degrees, and the degree of absolute value of x that appears is just fixed by rotation symmetry. Then there are some coefficients which appear, but line symmetry implies that these coefficients should be invariant tensors with indices M1, M2, M3, and M1L, where the collection M1L is traceless symmetric. And these coefficients are just constants, of course. But then what this is saying is that this set of coefficients is just kind of an invariant tensor of SO3, which takes spins J1, J2, and J3 into spin L. And so it's easy to understand that such invariant tensors can be expanded in terms of, like, you can find the basis for such invariant tensors in terms of 3J symbols, and the different elements of this basis are going to be labeled by the intermediate representation that appears here. And so in this way, you can kind of classify these tensors that can appear here, and using this, you basically get a new basis for your 3-point tensor structures, which is different from the basis I discussed before. but it's some convenient basis, and the reason it's convenient is because if you take a Fourier transform of such expression, you basically get again back the same expression times the new coefficient, because the functional dependence of with respect to p is completely fixed by rank symmetry. So what I'm trying to say here is there exists a choice of tensor structures such that you can compute this expression for x1 equals 0 and x2 equals infinity in a very simple way. And then if you can compute it in a simple way, you can apply the differential operator in a simple way. And then you can compare it with the result without applying differential operator, and you can extract these coefficients. So this new basis of tensor structures, we call it SO3 basis in our work, and it's some new basis of 3-point tensor structures in which these residue coefficients are especially simple. I mean, they're like not completely simple. There are some terrible expressions with like Clebsch-Gordan coefficients inside and square roots and programmers, but they're at least like explicit closed form expressions. And but this 3-point tensor structure base is not too bad, and you can work with it. Just that some properties are obscured. For example, if you want to permute J2 and J3, it becomes kind of complicated and so on. But even if you want to permute J1 and J2, actually there is a trouble because you put them at different points. But it turns out that it's not hard to relate this basis to something more nice like the Q basis I described before. And so you can live with this and work with this in practice. So using our expressions for this residue matrices, you can get closed forms homologic recursion relation for which works for any 3-dimensional conformal block. And so what this means is that you can now try to implement this in software, and that's what we have done in a recent paper with a similar set of collaborators. So we have implemented this algorithm in some open source software, which is called Blocks3D. So it's a relatively well documented thing. It has an accompanying paper. It has its own technical documentation. And its purpose in life is to compute all 3-dimensional conformal blocks. So it's something that's written in C++ and is relatively efficient. I mean, you can ask it to compute any conformal block. You can ask it to compute like conformal block with external spin 100 on each leg. And it's not going to do that because it's just going to take forever. But we have tried that it performs reasonably efficiently for conformal blocks up to including 4-stress tensor conformal blocks, which are probably the most complicated things anybody would want to compute in any distant future.
Sorry, and it computes these blocks exactly, yeah?
Well, it computes a power internally it computes a power series expansion in this R, but yes. As it is implemented now, right now it outputs polynomial approximations in terms of delta, so polynomials of delta for derivatives near this crossing symmetric point, because that's what you want for numerics. But like if somebody wants, for example, just the power series expansions themselves, it is possible to modify it slightly and make it output this power series expansion.
And sorry, Abhijit asked you this question, but I think my internet was a bit bad, then I missed it. That index over I, that sum over I runs over a finite number of variables?
Oh, it's infinite. Not, well, I is like I, you can think of it as a n. So n runs from 0 to infinity, and a is like runs from 1 to 4. There are like 4 families, and well, actually, in any conformal block, only 3 families have infinite remaining non-zero residues, and 1 family has only finite remaining non-zero residues.
Oh, so n's are like the descendants of the null primary state?
No, so each null primary appears. So each null primary, only null primaries appear. Each null primary appears once, but they appear at different delta i's. So there's delta I for each possible null primary that can happen.
And that's a finite number, right?
No, that's an infinite number. It's not. They're not appearing at the same time. They're appearing in different values of delta. So if delta approaches a particular pole, then a particular null primary appears.
So this infinity goes, delta I goes to minus infinity as I increases?
Yes, precisely.
Okay, so there are, I see.
So in this,
but these are subleading in R.
Yeah, precisely. So this ni goes to infinity, and well, it's the same n, and it actually starts from 1 in this notation.
And sorry, I should have known this. I should have known that there is an infinite number of places where you get, I mean, when you go away from unitarity, there's infinite number of places where I get null states. Somehow I didn't know this.
Yeah, is there any interpretation? Is there a way to understand this?
Well, there is a simple way to convince yourself that this must be true. So let me give you an example with SL2R. So SL2R, you have like it's one-dimensional conformal group. So its unitarity condition is that delta is positive, right? But SL2R also has finite dimensional representations, right? Of spin J. So you can ask what is the what does it mean in terms of delta? Delta equals minus J. So for every negative integer, there is a kind of pole corresponding to the fact that like the Verma module, which if you set delta to negative integer, the Verma module that you built is infinite dimensional, but you can cut it off to make it finite dimensional. So there are infinitely many null descendants, and if you set them to 0, you're left with finite dimensional representation.
I see. And
is it also
sorry, higher and higher n are descendants at higher and higher level with more and more p operators acting on the primary?
Yes, exactly. And this n is just the number of p operators. So it goes
right, now I understand. Okay, I understand. So you get some higher and higher equation. So, if you do it at nth order and p, you'd get an equation in delta which is a polynomial of order n.
So sorry, can you repeat the question?
Suppose I asked for the condition for having an nth level descendant being null.
Yes, you get polynomial in delta.
Right. So you put np's, then you put nk's, and you use the pk commutation relations. Each of them will give you a delta. So you'll get some equation in delta which is of order n. Right? You get and that will have n roots typically.
Yes.
So you would label so these places where it would happen would be labeled by what order in, you know, how far down, so how many p's and which root.
So you have to take so the reason it grows with n is that, roughly speaking, at every n you can only get one descendant. Now at every n you can get one. I think it's true that at every n you can get order 1 null primary descendants.
Now
but if you ask about null descendants, they also receive contributions from all.
Yes, I understand. You say that the solutions you get at level n will include all the solutions you've got from 1 to n-1.
Yes, exactly.
But one more, because it's nth degree polynomial.
Yes.
So at each level you'll get one extra one. Okay, yes, I understand. Thank you. Okay, beautiful. Yes.
Finitely many extra ones because you have matrices. It's
okay,
not,
fine.
In SL2R, yes, just one, but in higher dimensions, finitely many new ones.
I understand. If you were working with scalar primaries, you would get one at every level.
Still no, because P is
there's momentum. Yeah.
Momentum, but that the indices contract.
No, so descendant is P mu1, P mu2, blah, 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 P mu n. So descendant is like P mu1.
Right.
P mu n.
And then you put the same case on the other side.
you put different case because
Oh, yeah, and then you want that the matrix is positive definite. Okay, fine.
yeah.
Okay. So what K are you talking about?
Oh, when you take conjugate, you get case.
Oh, okay. Yeah. To compute the norm. Okay, I see.
Yeah, exactly.
So, one question.
Yeah, sorry, go ahead.
No, just this analogy with SL2, is it also that in higher dimensional conformal groups, these null states can be traced to representations of the compact counterparts?
Sorry.
In the SL2, those are representations of SU2, right? The compact counterpart of SL2. So is it that these representations I should think of somehow as representations of the compact ones? Are they related to that? No, I guess not. Because these are not finite representations, right? These are, I guess not, yeah.
So the special thing that happens in SL2R is that the quotient of the Fermat module by the null states is finite dimensional. So there are examples like this in higher dimensions as well, but not every example is of this form.
I see. But where there is an example that presumably is a compact representation.
Yeah, those
are finite
dimensions. Yeah, those are compact representations. I just wanted to say that a simple toy model for this is SL2R conformal block. It's just hypergeometric to F1. So its poles are coming from the programmer from this index when delta is negative, right? Because it will have an expansion, it will have some n, and then it will have n factorial, and then there's going to be delta n squared, and then 2 delta n. Sorry. Delta n. So it's sufficiently high level. So you can check in this expansion all these things that we discussed, that how number of descendants goes, that they happen negative deltas and so on. And you can check that you can also check this explicitly. This function satisfies it after you factor out this R to the delta.
I see. And you said all these H functions were known exactly?
H infinity is unknown. Well, they were not known before our work, but we found a way to compute them for any spins.
So I see. So are these H's roughly what you would get by exchanging the primary by exchanging the null states?
So which H are you talking about? The H infinity one or the other one?
No, the second one, H delta INI.
That is the block of that guy.
Sorry, I missed here. There's an index J also, of course. So this is one function, right? This function H is defined in terms of conformal blocks. So they only differ by simple power. This is because blocks behave as R to the delta. You need to factor that out. After that, you just get this thing, and knowing it is equivalent to knowing the conformal block. Now it has a finite limit as delta goes to infinity, which we call H infinity. So this limit is easy to compute because it's just asymptotic, and you can compute conformal blocks in higher dimensions by solving Casimir equation. So Casimir equation in general is hard to solve, but it's easy to solve to the first few leading orders in delta. And that's what you need to get this H infinity.
Okay, but what about the H delta NIs on the right-hand side? You're
asking what to do with them?
Yes.
So you plug in the left, like you plug the expression into itself, and you keep doing that. And because this, you have R to the positive powers, the things that you don't know get shifted to higher and higher powers of R.
I see.
So if you do this like 20 times, then the first stage that you don't know will appear at only R to the 20.
Okay.
And so you will know everything until then. And you just repeat this recursion.
That's very beautiful.
That's how it works.
Yeah. So the H, the guys on the right-hand side are the conformal blocks for exchanging the primary operator that labels the null states, right?
So on the left-hand side, we're exchanging some primary operator. On the right-hand side, these guys are the conformal blocks for exchanging the null primary.
Exactly. Okay, excellent. And one more question. The reason that you get this divergence at delta equals delta I is that the conformal blocks has this division by the 2-point functions.
Yes.
Which blows up when the guy goes null, right?
Yeah. Precisely because of this.
Okay. Oh, it's very beautiful. It's a very beautiful structure. So, and you said this structure was explored by Zamolodchikov?
So Zamolodchikov explored it for various other conformal blocks in 2D. So he actually explored two structures. So one structure is exactly like this, and the other structure is varying central charge. So you keep a delta fixed and you vary the central charge. So then you can, when you vary central charge, the null states in the reservoir blocks move, and sometimes they hit your delta that you keep fixed. So he has two expressions as a meromorphic function of delta and as a meromorphic function of central charge.
Okay, and its generalizations to above 2 dimensions, that is your work?
No, so first the generalization to above 2 dimensions was done by Simon Zdaff in Poland and Philip Koss in their work on numerical bootstrap of ON models, I think, like the first of the papers. And then there was some kind of more general paper by Pinedonius, Trevisani, and Masahito, which discussed this theory, but like our contribution was to find the closed form for this guys.
Okay, and sorry, one last. If you were really exchanging a null state, a short representation, say we were really exchanging a conserved current, then you would get the conformal block by dropping the pole corresponding to that conserved to that null state. Right?
So very good. So what happens when you're exchanging a conformal conserved current is that if you look at the 3-point functions, so let's say this 3-point functions. So the differential operator that you're interested in is the conservation differential operator. So the only 3-point functions that are like the OP coefficients are constrained that such that the physical 3-point functions are conserved, which means that when you multiply this by your OP coefficients and you sum over A, you should get 0. Which means that your P coefficients are a null vector, like live in the kernel of this Ri.
Right.
Which means that when you multiply it in this recursion, then yes, this residues will vanish because of the form that your P coefficients take.
Right. So effectively, you just drop the pole, the offending pole.
Yes.
And keep everything else, and that's the right answer. Okay. Yeah. Thank you.
So, for SL2, what is the residue at delta equal to J for this this conformal block? Is it some character of the representation, SU2 representation?
No. So sorry, you're asking what is the residue or what is the coefficient? Because residue is again this hypergeometric function. Shifted argument, and the coefficient is some simple thing like some factorial of J or something. We don't know that
I should see somehow the SU2 representations, right? So I was wondering if there is a way to write this down in terms of SU2 characters.
Well, I don't know, maybe. I'm not sure. Could
is it because you are not quotienting the right hand side?
Oh, I see what you're saying. So the thing that appears as a residue is not the block of the finite dimensional representation, is the block of the thing that you need to throw away in order to get a finite dimensional representation.
Yeah, right.
So, yeah. Okay. So I'm not sure.
Okay, thanks.
Okay, one more question, probably very stupid. When when the operator that is exchanged has infinite dimension, why aren't we getting some infinite power of Z and Z bar?
Oh, we're getting it. We're just factoring it out.
I see.
That's why I do it. And it's important to factor out R like this. It's some function of Z and Z bar, not just Z and Z bar, because it's not just that the primary is the dominating term. It's all descendants also contribute significantly at a large delta.
Okay, thank you. Thank you. Yeah.
Oh, I see. So you're saying even for the H infinity, the H calculating and H infinity is important. I mean, can I not think of this as that contribution being negligible at R equal to 0.17?
No, H infinity is important. So you need to know the R expansion of H infinity in order to get the result. So H infinity is important. You need to compute it, and the way you do this is by solving Casimir equation at leading order in delta. And actually, I mean, it's another thing that we did for the first time in our paper, because it turned out that this basis that we introduced here. So here, if you choose these Qs to be eigenvalues, so if you choose these Qs to be the eigenvalues of rotations inside this plane, so it's kind of labeling by the 2D-dimensional spins. Then it turns out that this basis diagonalizes the Casimir equation for the first two orders in delta, which is precisely the right amount to be able to solve for this H infinity. So in general, Casimir equation would be a differential equation, which is some matrix in this index I, which is hard to solve. But in this specific basis, it diagonalizes to the first two orders in delta, so you can solve it. So the first order in delta gives you this power, and the second order in delta gives you this function. So you can find everything nice. And all this actually generalizes to higher dimensions. It's not necessary. There's one exception I should, by the way, forgot to say. So this expression is true in even dimensions. Sorry, in odd dimensions, in odd number of dimensions. In even number of dimensions, you can get double poles. So you can get delta minus delta I squared. And this has to do with the fact that it can happen that you have two primary, if I understand correctly, it's connected to the fact that you can have two null descendants at the same time, two null primaries at the same time in the Fermat module. And then their intersection is like doubly null in some sense. And this leads to double poles. So the coefficient of the double pole is still conformal block. Coefficient of the single pole is something more complicated, which there is no good theory about it, so it's an open problem. It's like you can work out this for scalar blocks. You can just explicitly work out this recursion relation as a limit from generic D. But for like, I'm not aware of any mathematical theory, so it would be interesting to understand it. So there are things about this that we don't understand. But besides this problem, like if you ignore even dimensions for which we don't have a good theory, if you want to do it in 5 dimensions, so all these techniques that I discussed, they generalize to 5 dimensions. Just that because Lorentz group in 3 dimensions is SO3, which is extremely simple, and Lorentz group in 5 dimensions is SO5, which is still simple group, but it's much more complicated simple group. So the formulas become much more tedious, and we don't have them, but in principle you could derive them. So that's the start of this thing. And yes, and as I said, we implemented it in the software, which can just compute for you any conformal block. And it's nice. And also we have made it so that this software works very nicely with the Haskell libraries. So if you're using this Haskell libraries, you just have to tell it where to find this program, and then you don't have to think about calling it. You can just write your equations and not think about computing conformal blocks because that's all taken care of. So that kind of brings me to my sort of exaggerated summary, which is this, that basically, as of now, there's lots of caveats, but still, I think to a large extent true. If you want to do any three-dimensional numerical bootstrap problem, all you need to do is to download some code, write your kind of what you want to do in terms of some high-level equations, and hit enter, and it will work. Of course, you still need, like, we actually have not implemented supersymmetric equations because we don't know supersymmetric blocks in general, so that's one open problem. But of course, you still, need to apply for cluster time. You still need to deal with all the things which come when you start doing things numerically. You have to be careful not to try to compute something which is too hard for your performance and so on. But as far as computing special functions which should be computed by microprocessors and not humans goes, it's a solved problem. And so I think to a large extent, anybody who wants to work on any 3D, at least numerical bootstrap, it's very easy to do so now. So if you're interested, please do, and I think all the tools are here. So in the future, in the future, we'd like to finish our work on Gross-Neveu-Yukawa model, and so we're going to hire NMAX to get tighter bounds and also exploring other bounds. It would be interesting to also study mixed systems with stress tensor, for example. It could be interesting to take the bootstrap setup for three-dimensional Ising model and add stress tensor there, because then you could study the TTOP in this model, and then maybe you can, for example, compute energy-energy correlators, like conformal collider correlators in Ising CFT, so which would be interesting to some extent. And another obvious goal is to do bounds for non-abelian currents, where you just take 4 non-abelian currents and you don't assume anything else. And in this way, you can put some constraints on any theory of the global symmetry by assuming what this global symmetry group is. And you can explore what different global symmetry groups mean for the bounds in various operator dimensions, central charges, and so on. And I think this particular direction is also interesting to extend to 4D, because there the 3-point functions of current non-abelian currents contain triangle anomalies, and so you can also then connect these bounds to the anomalies, which are one of the very few things that we actually can compute and result supersymmetry. So, and of course, there are lots of other prospects. There are very likely many more three-dimensional theories which you can tackle with these techniques. It's still an open problem to understand, for example, conformal gauge theories in 3D. So I think there's lots of work to do, and we have now all the tools needed for that. So thank you. Sorry for going over time, and I'll stop here.
Thank you very much, Petr, for a very nice talk. We have questions?
So I have one embarrassing question. I'm sorry to ask this so late, but there was this parameter R that you had in your recursion relation.
Yep.
Could you say what R was like Z? Sorry, what was R?
So R is square root of a rho bar, where rho is this function of Z. So the meaning of R is that, the usual meaning of Z is that if you put a point at at 0, operator at 0, operator at 1, and operator at infinity, so 1, 3, 4, then the second operator would be at Z. So that's the meaning of Z. So the meaning of R is that if you put operator 1, operator 4 at -1, operator 3 at +1, then you put operator 2 at row, and then operator 1 at minus row. So it's kind of a symmetric configuration. Then R is just this absolute value of row.
Okay. And
let me just say the conformal block expansion converges for R less than 1. So this is the region of convergence to conformal block expansion. In some sense, you're not that interested in conformal blocks with R greater than 1.
I see. I see. What I'm not understanding, at least if what I'm not understanding intuitively, is why this expansion in higher and higher null states. Why do you have this R to the power n outside here?
Oh, it's very simple, because this is an equality, like function equals sum over poles, but you can write a simpler statement that H delta near a pole looks like some coefficient R times H delta I plus Ni, right? And then there's going to be this R to Ni thing. So this equation, you can, unlike this recursion relation, this statement, you can just write in terms of G. And if you write it in terms of G, then it will be just this. It will be just conformal block has a pole where the residue is another conformal block. And the way this R to the n appears, this R to the n appears just because you factored it out of the conformal block. So if you plug this definition here, then R to the n will appear because the conformal blocks have different arguments near the pole, different values of delta. So it's conformal blocks for conformal, like if you try to write this equation for conformal blocks for G instead of H, then there will be no factor like this. But then this equation will be wrong because unlike H, conformal blocks actually have an essential singularity in infinity.
Okay. So is one way of saying it that the reason that it's good to work with these conformal blocks with R to the power delta scaled out is that that's the object that has good delta equals infinity limit.
Yeah.
Okay. Interesting. Very interesting. Thank you.
Are there more questions? If not, let's thank Peter again for a very nice talk.
That was really very interesting. Thank you so much.
Well, thank you for all the questions. It's always much more fun when people are interested in ask questions.
Okay. Yeah.
Bye-bye.
Right.
Thanks.
Bye. Have a good day.